Right, hello everyone. Thank you for joining me today. It's an exciting time for both the OCP community and the CXL community over the last number of months here. CXL really started a few years ago as a concept, a number of specifications coming through. We made a lot of advancements over the last few years, and it's exciting to now finally take it from what a concept, a promise that it was, to the reality that we have today with a lot of silicon. So I want to walk you through exactly how we're deploying these solutions today and what the next little overlook is going to look like. So my name is Ahmad Danesh. I'm the Senior Director of Product Management at Astera Labs. And today we're going to walk you through a few things here. Start off taking a look at the AI and ML high performance infrastructure. What's actually needed to start deploying these things? What are the challenges that we actually face in the infrastructure? Give a quick introduction to Astera Labs, but really we're going to be focusing most of our conversation on memory bottlenecks in the data center. How is CXL actually starting to solve these problems today? We'll take a look at memory expansion solutions, we'll take a look at memory pooling solutions, and then we'll end off with a call to action and how we can, as a community, take this to the next step. So when we take a look at the AI and ML workloads that are needed to really drive through the cloud infrastructure, we see that cloud is fundamentally the new core. About half of our data is now in the cloud. It's going to be in the cloud in 2025. And what that really requires is high performance, low latency interconnects to be able to connect all of the various compute, memory, storage, and networking infrastructure that's needed. Now, when we specifically take a look at AI and ML, what we've been seeing is the actual models and the data sets themselves have been getting more and more complex. They've been doubling every 3.5 months, far outpacing Moore's Law, and that requires a new look at how we actually solve these problems. We can't just start increasing the speeds and expect that to solve what we need for these complex AI and ML workloads. And fundamentally what that means for all of us in the room and why we're here as a community is there's a big opportunity for all of us in this space, and we work together both within the OCP community and the CXL community to take these solutions to market and really start taking advantage of the new technologies that are being advanced. And this comes through in three ways. One is fundamentally the memory connectivity itself. We're going to be focusing most of our presentation on memory, but fundamentally the compute infrastructure is of course very important to this, and how the compute is interconnected to the memory and how we can actually start creating heterogeneous architectures. And then of course on the networking side as well. How do we actually interconnect all of these pieces together so you can get access to that data? When we take a look at the memory, the fundamental problems that we're trying to solve, and we'll dive deeper in a second on this, is that modern CPUs and GPUs need more memory. That comes in both capacity expansion and bandwidth expansion to serve those workloads. And when we get to the compute infrastructure, we start taking a look at how do we create heterogeneous architectures to actually interconnect all these various pieces together and increase the utilization of the resources that we're deploying. Fundamentally, we want to increase the performance for those workloads, but we also want to take a look at how are we actually reducing the costs as well and maximizing the resources that we actually deploy in the data center as we scale these solutions. And on the networking side, we're seeing that the speeds are doubling every roughly 24 months. And so what is the infrastructure needed as we take this to the next step? So Astera Labs, we build connectivity solutions to solve these data and memory bottlenecks. Within the memory space, we have our Leo platform. Leo is a CXL memory controller that provides CXL connectivity to DDR5 DRAM to solve memory expansion and memory pooling. We'll walk through exactly how it does it in a few slides here. In compute infrastructure, what we do is we have our Aries platform to increase the bandwidth, as well as taking a look at low latency connectivity as we're progressing to, from Gen 3, of course, to PCIe Gen 4 that's being deployed broadly today, and as we now move forward into deploying PCIe Gen 5 solutions. But as we get to PCIe Gen 5, that's where CXL starts coming into the picture as well. So we want to make sure we have that low latency connectivity that's needed for both CXL memory expansion and pooling solutions. And then finally on networking, taking a look at, as we start increasing the speeds, how do we start increasing it while still being able to service this across racks? And we're going to start seeing a transition where we're going to see a lot more active copper solutions, and our solutions there that are solving that. But fundamentally, we're going to really focus in on memory today. So let's start by understanding what are the actual bottlenecks that we're trying to solve. The first, and I touched on this earlier, is that the actual model complexity is doubling every 3.5 months. What that means is those models need more access to memory capacity, and they need more memory bandwidth as well. But unfortunately, as we've taken a look over the last 10 years, CPU core counts continue to increase, but the actual memory bandwidth per core has been declining year over year for the past 10 years. Now, of course, we all want to increase the memory bandwidth and capacity. How do we do that? Unfortunately, with server CPUs, there are some physical constraints that we can't get through. Right? There are going to be package and thermal constraints that fundamentally limit the number of local DDR channels a CPU can have. And then finally, when we take a look at memory today, it's really tied to a compute node. What that means is that depending on the workload, some of that memory capacity and bandwidth actually isn't being utilized. And so when we take a look at an instantaneous time, we'll see that a lot of capacity isn't being used by those CPU cores, especially in the case of when you have virtual machines that are being rented out. The cores have been rented out, a lot of the memory has been rented out, so there's no more cores that can be rented to that virtual machine, but there's a number of memory capacity that's not being used. We're going to actually be doing a lot more into memory pooling and some future presentations as well, but let's take a look at how we actually solve these. So for the first three problems I was describing, fundamentally what we need is more memory bandwidth, more memory capacity, and that's what we refer to as CXL memory expansion. For the last problem, in terms of memory being stranded, the intention here is create heterogeneous architectures of multiple CPUs that can access a common memory pool. And that's where CXL memory pooling comes into the picture. So we'll start off with memory expansion. And the concept is simple. Let's take CXL interface, a serial bus, and allow whether that's CPUs, GPUs, or accelerators to be able to expand memory beyond the local memory that they have, whether that's local DDR, or in the case of GPUs, HBM. Of course, HBM is very expensive. Some workloads could actually just use a lot more capacity, and that's where CXL can come in, create that higher bandwidth. But what's extremely important here is that it's ultra low latency. And the CXL protocol allows us to do that as long as you have the right architecture and silicon to do so. And what's great is over the last number of years with CXL 1.1 being released, we're finally here with actual real silicon and able to show the actual performance that these solutions deliver. So we actually have CXL 1.1 memory expansion in the show right now, working with the 4th gen Intel Xeon processors. And for cases where you do need extended reach, where this is going to become important is as we start scaling this out, as we want to get more and more CXL devices in the path, and as we start going to PCIe Gen 5 rates, in some cases you might need a retimer to be able to get to those those devices, creating larger systems. And putting this together, what this allows us to do is increase memory bandwidth and capacity with an additional 12 to 24 more DIMMs per server. This is a significant step. So in that previous diagram where I showed the memory bandwidth per core declining year over year, we can suddenly take a nice step up in that and solve that memory expansion problem. So the question is, well, what happens if you add a CXL memory controller in the path? What is the impact to your performance? And so what we're showcasing here is actually running a very common use case, an in-memory database application where you can run a mem-tier benchmark. And we can see that CXL performs almost the same as local memory. This really starts opening the door so that we don't have to worry about the latency of the solution. Now, of course, every workload is going to be different. Every workload has a different sensitivity in terms of the bandwidth sensitivity, capacity sensitivity, or latency sensitivity. And so we're going to see a really interesting result as we start scaling this out, adding a lot more CXL memory controllers in the path, adding that to the local DRAM, and really taking advantage of that expanded bandwidth that it provides. So next, let's take a look at CXL memory pooling and fundamentally what we're trying to solve there. The intention of memory pooling is slightly different than memory expansion. The intention here is we want to take multiple CPUs, all connected to the same memory controller, and be able to allocate dynamically the memory that sits behind that CXL memory controller to the CPUs, GPUs, or accelerators. In the diagram that's playing right now, what you're seeing is that it's actually just being split 50-50. But in order to really be able to take advantage, what you want to do is dynamically change this. And we're able to do that now. We can actually dynamically deploy this in such a way that after the CPUs are running, you can actually deallocate memory from one CPU, sanitize that memory, because security is obviously important if you don't want to give that memory access to another CPU before sanitizing and clearing that data, and allocate it to another CPU. This suddenly opens the door. We don't have to worry about memory being tied to a single compute node. And similar to how I was showing on the memory expansion case, we're finally here now as well. We actually have real silicon that's running with multiple CPUs, again, those 2 Intel Xeon processors with our Leo memory connectivity controllers, and being able to pool memory across these multiple CPUs. This fundamentally allows us to reduce memory stranding with CXL 1.1 capable CPUs. A lot of people in the industry have been asking, well, didn't memory pooling get introduced in CXL 2.0 specification? And yes, it did. It got introduced in that specification with the ability to use it with the CXL switch. The challenge with the CXL switch is that you add even more latency. You now have a CXL switch hop as well as a memory controller hop. That added latency reduces the number of workloads that it can be beneficial for. So doing it in such a way where you have multi-ported, or what the CXL spec calls multi-headed memory controllers, you can reduce that CXL switch hop, reduce the latency, and be able to service more workloads. And ultimately, the end goal being you want to increase the utilization of all the resources that you've deployed, in this case, the memory resources, and reduce your total cost of ownership. So as we move forward here, obviously do join us at the booth if you'd like to see these demos in action. There's a lot of work happening across the ecosystem, and we're working with some really key partners to deploy these solutions. So ourselves, Microsoft and Google, we're giving a presentation tomorrow focused in on memory pooling. Please do join us. There's actually going to be an entire CXL forum where we're actually walking through everything from memory expansion, memory pooling, teaching everyone about CXL 1.1, all the way to CXL 3.0 specification, and how as an industry we're coming together to deploy these solutions. And actually deploying them is going to require some dedicated hardware. It's going to take software. In the case of memory pooling, who orchestrates this system? How does one CPU get access to that additional memory pool? A lot of this work is happening in the community right now, both within OCP and CXL, and within OCP specifically in the software-defined memory working group. So please do join us, and we'll look forward to working with you. Thank you.